We intuitively model planets as passive objects, quiet spheres of rock or gas bound by gravity, drifting in the cold vacuum. But planetary environments are not static sculptures. They are thermodynamic machines. When a planet is pushed out of the narrow temperate zone and dropped into an extreme gravitational or thermal gradient, passive geology vanishes. Chemistry converts into raw, aggressive mechanical action. At the boundaries of astrophysics, an atmosphere is not merely a blanket of air. It becomes an engine of shredded molecules, supersonic glass, and liquid metal. These mechanics are not theoretical extrapolations. They are the strict, observable consequences of the periodic table reacting to severe thermodynamic stress. For centuries, planetary science suffered from a sample size of exactly 8. Because we only had our solar system to study, we built a rigid baseline blueprint. Rocky worlds huddled near the star, gas giants exiled to the cold outer rim, all locked in stable, circular orbits. We assumed the universe shared our architecture. That assumption shifted permanently with transit photometry. As space telescopes began staring at distant stars, they detected microscopic dips in starlight, shadows cast by planets passing in front of their host stars. By analyzing the spectra of light filtering through the edges of these shadows, we didn't just find new planets. We found physical models pushed to their absolute limits. We discovered gas giants orbiting so close to their stars that their years are measured in hours. We found atmospheres that absorb light like a sponge and worlds older than the heavy elements required to build them. To map reality accurately, we cannot look away from these extremes. We have to dissect the mechanisms driving them. Consider WASP-76b, a massive gas giant located 640 light-years away. It sits so close to its host star that extreme gravitational tides have locked its rotation. One hemisphere faces a permanent, blazing day. The other is trapped in eternal, freezing night. This creates a catastrophic thermal gradient. On the day side, temperatures blast past 2,400 degrees Celsius. At this energy threshold, the sheer heat overcomes the metallic bonds of the iron lattice, vaporizing the metal directly into a heavy atomic gas. We know this because when telescopes analyze the light filtering through the planet's evening terminator, the border where day turns to night, they detect the clear, undeniable spectral signature of iron vapor. But on the morning terminator, where night turns back to day, that iron signature completely vanishes. The iron is missing. The leading atmospheric model to explain this asymmetry is a rapid phase change. As the vaporized iron is swept by supersonic winds into the freezing night side, it is theorized to condense back into liquid droplets. If this model holds true, the atmosphere operates a torrential, continuous storm of liquid iron rain falling into the deep, churning, gaseous interior. Yet, liquid metal is not the only exotic downpour waiting in the cosmic dark. 63 light-years away sits HD 189733b. Through a telescope, it might appear as a serene, deep blue marble. But that blue signature is not the reflection of a calm ocean. It is the optical scattering of light bouncing off an atmosphere heavily saturated with microscopic silicate particles. Due to the planet's severe proximity to its star, the atmosphere is superheated, driving equatorial wind jets that likely exceed 8,000 kilometers per hour, roughly 7 times the speed of sound. Under this extreme heat, observational models suggest the suspended silicates condense into airborne droplets of liquid glass. Because of the immense kinetic energy of these supersonic winds, this glass does not fall vertically under the pull of gravity. It is whipped horizontally. The atmosphere operates as a perpetual, planet-wide storm of glass rain, slicing sideways through the air. The physical shear forces would shred standard materials in seconds. Here, kinetic energy dominates the environment. But even horizontal glass storms rely on atoms staying bound together as molecules. There is a thermal threshold where that fundamental rule collapses. If you push thermal energy beyond standard planetary limits, you reach KELT-9b. The day side of this planet reaches an incomprehensible 4,600 Kelvin, hotter than the surface of most red dwarf stars. At this temperature, the standard rules of atmospheric chemistry fail. Molecular hydrogen, the basic building block of gas giants, cannot survive intact. The intense thermal energy is so severe it overcomes the binding energy of the molecule. On the day side, hydrogen molecules are thermally dissociated, torn apart into solitary hydrogen atoms. This creates a planetary atomic engine. The dissociated atoms are pushed by atmospheric currents to the cooler night side. As the temperature drops, they rapidly recombine into molecules, releasing massive amounts of latent heat energy into the dark hemisphere. Then, the winds carry them back to the day side to be dissociated all over again. KELT-9b functions as a global heat pump, running continuously on the destruction and assembly of molecular bonds. After observing molecules tearing themselves apart, it is tempting to assume that extreme heat always produces blazing, volatile chaos. But as we move deeper into the exoplanet catalog, we encounter a much more unsettling extreme: worlds that break our chemical models entirely. Consider TRES-2b, an ultra-hot gas giant that presents a profound thermodynamic paradox. TRES-2b reflects less than 1% of the starlight that hits it, making it significantly darker than coal or black acrylic paint. Current spectroscopic models suggest its atmosphere might contain vaporized alkali metals like sodium and potassium alongside titanium oxide. These elements act as optical sponges, absorbing visible wavelengths. But here is where the model fractures. Even factoring in those optical sponges, astronomers calculate that the planet should still reflect more light than it does. The chemical inventory we understand cannot fully account for the total absence of reflection. TRES-2b isn't just dark, it is darker than our current physics predict, actively swallowing photons through an atmospheric mechanism we have yet to successfully map. Every bizarre mechanism we've explored so far operates in the present, driven by the intense radiation of living, burning stars. But what happens when the star itself dies? Does planetary mechanics end? To answer that, we must escalate from extremes of chemistry to the extremes of deep cosmic time. 13,000 light-years away lies PSRB 1620-26b, nicknamed Methuselah. Observational data places this planet at roughly 12.7 billion years old. It formed just 1 billion years after the Big Bang. This age forces a massive shift in our accretion models, offering compelling evidence that planets were successfully assembling in a primordial metal-poor cosmos long before our solar system existed. But more staggeringly, Methuselah orbits a dead binary system, a rapidly spinning pulsar and a burned-out white dwarf. To exist today, this ancient mass had to survive the apocalyptic supernova that created the pulsar, the massive stellar expansion that created the white dwarf, and the violent gravitational capture that bound them all together. It proves that a planet is not merely a byproduct of a living star. Under the right conditions, a planet can outlive the death of its host, enduring as a gravitationally immortal ghost long after the light goes out. When we look closely at these extreme exoplanets, we must abandon the idea that they are impossible anomalies or cosmic mistakes. They are the strict, logical outcomes of physical laws operating under severe thermodynamic stress, executing their mechanics across extreme gradients of pressure and time. Our solar system is not the standard template of the universe. Earth is a brief, incredibly delicate middle ground, a remarkably narrow thermal window where water remains a calm liquid. Our chemical models hold true, and iron stays safely buried in the crust, rather than falling violently from the sky. In a universe governed by extreme mechanical violence, a quiet world is the true anomaly. We've spent today exploring planetary nightmares where iron rains from the sky and glass flies at supersonic speeds. But if violent chaos is the cosmic norm, where are the rare, quiet worlds that could actually host life? Subscribe to join us as we search for those hidden sanctuaries in the next video, and check out our shorts for daily, bite-sized deep dives into the universe's most curious questions.